Okay, let me continue the Newton-Cots formula. Newton-Cots formula, and before I give you some examples for special cases, let me explain two very important theorems about the error term of the formula. So I should state two main theorems about the error for the closed and for the open Newton-Cots formula. First, let me explain the error for closed Newton-Cots formula. Let x0 be equal to a, xn be equal to b, and h be equal to b minus a over n. Okay? And for each I between 0 and n, we have xi is equal to a, in fact x0 plus ih, okay, for I equal to 0, 1 to n. Okay, so closed Newton-Cots formula is sigma I from 0 to n ai fi. This is n plus 1 points closed Newton formula, Newton-Cots formula. Then there exists eta in the interval, closed interval a and b, such that we have two cases. Case 1, if n be divisible on 2 and f belong to Cn plus 2 a and b, it means that f and the derivative of f up to n plus 2 order are exist and continuous. Okay, then integral from a to b f of x d of x be equal to sum I from 0 to n ai fi, which we have computed ai's, but the important things here is the new term, in fact the error term here, h to power of n plus 3 over n plus 2 factorial, n plus 2 derivative of f at eta, integral from 0 to n t times I equal to 0 to n pi I equal to 0 to n t minus I d of t. This is for the case that n is divisible on 2. Okay? But if in the second case, if n is not divisible on 2 and f belong to Cn plus 1 on the interval a and b, in this case we will have integral from a to b f of x d of x is equal to I from 0 to n ai fi, that we have computed ai's, plus this is the important term, h to power of n plus 2 over n plus 1 factorial, yeah, n plus 1th derivative of f at eta integral from 0 to n pi t minus I for I equal to n d of t. This is the first theorem about the error term for the closed Newton-Cots formula. Okay? Now, we have something very, very similar to this theorem, just some very simple changes. Let me do the changes here. We say that let x minus 1 be equal to a and xn plus 1 be equal to b and h be equal to b minus a over n minus 2, n plus 2, sorry. Then for each I between 0 and n, we have xi equal to x minus 1 plus ah for I equal to 0 to n. Okay? So this is in fact open. Newton-Cots formula is something like this. Then there existed an eta in the interval a and b, such that if n is divisible on 2 and f belongs to cn plus 2 over a and b, then the integral is equal to this one, and this one is same, and the difference is in in fact the bounds of interval minus 1 to n plus 1, integral from minus 1 to n plus 1 here, and just exactly everything is like this, and just here this is minus 1 to n plus 1 and nothing more. This is the error term for the open Newton-Cots formula. Okay? Please put these two formula in your mind. I will use all of these formula later. So, now let me give you some examples. Okay? Examples. Example number 1. Let n be equal to 1. Okay? If n be equal to 1, so we have to consider 2 points, x0 and x1. So I say consider x0 and x1 as 2 points. Okay? When we have n equal to 1, in fact, we want to compute the trapezoidal integration formula again, but with the new method, with the Newton-Cots method. Okay? So, in fact, we can put x0 is equal to x0 plus 0h, and x1 is x0 plus 1h. Okay? These two relations gives me that p is equal to 0 and q is equal to 1. Okay? Now we have to compute ai's. Okay? In fact, a0 and a1. So let me write. We have to compute a0 and a1. Remember that we had ai be equal to h times minus 1 to power of n minus I over n factorial combination I from n integral from p to q pi k equal to 0 to n s minus k over s minus I d of s for I equal to 0, 1, 2 and to n. Okay, so if I want to compute A0, so A0 is H. Note that N is equal to 1, okay, and I equal to 0. So A0 is H. If we write H here and use exactly this formula, minus 1 to power of 1 minus 0 over 1 factorial combination 0 from 1 integral from 0 to 1. P and Q are computed here. Look, okay? So here, K from 0 to 1. Okay, from 0 to 1, in fact, this means that S minus 0 times S minus 1 over S minus 0, I is 0, right? D of S. Okay, now let me do some simplification. This minus 1, 1 minus H, and this is 1, so I will have 1 minus H from all of this term, and here S will cancel with S and remain 0 to 1, S minus 1 D of S. Okay, so I have to compute this integral. If I do the integral, I will have minus H times half squared minus S from 0 to 1, and this is minus H times half minus 1 minus 0 plus 0. Okay, and this is half H, this is H over 2. Keep it. This is A0. And exactly in the same way, I want to compute A1. Note that N equal to 1, I equal to 1. So A1 is H minus 1 to power of 1 minus I, 1 minus 1 over 1 factorial combination 1 of 1. Integral from 0 to 1, S minus 0 times S minus 1 over S minus 1 D of S. If you compute here, this is H. Just keep it. Integral from 0 to 1, cancel these two, and this is S, D of S, this is H, 1 half squared from 0 to 1, and this is H times half, this is H over 2. And also keep it in your mind. So the integral from A to B is to form A0 F0. A0 is H over 2 F0 plus A1 F1. A1 is H over 2 F1. Okay? Plus error term. And if you factor H over 2, you will have F0 plus F1 plus error term. This first part of this formula, this is exactly the trapezoidal integration formula, and now we want to compute E. Okay, we want to compute E. If I want to compute E, I have to use the, in fact, error term that I showed you before. Look at the theorem. We are using the closed Newton-Cots formula. Here, the black part of this theorem. N is equal to 1, so N is not divisible by 2. So I have to use this part for the, in fact, error term, right? I have to use this part. Let me rewrite here. So, for E, we note that N is equal to 1 and 1 is not divisible by 2. So E is equal to h to power of n plus 2 over n plus 1 factorial fn plus 1 eta times 0 to n pi I from 0 to n t minus I d of t. Okay? Now, let me use n equal to 1. So, E is equal to, here, put instead of n, 1. So, E is h to power of 1 plus 2. This is 3 over 2 factorial, right? F 1 plus 1, f double prime eta, integral from 0 to 1. And this pi is 0 to 1, so I have just t times t minus 1, right? D of t. I keep h squared over 2 f double prime at eta and compute this integral. Okay, this integral is, if you take integral, is 1 over 3 squared minus 1 over 2 squared. This is cube, in fact, not squared. From 0 to 1, right? And let me do some simplification. This is h over 3 over 2 f double prime at eta times 1 over 3 minus 1 over 2. And this is minus h cube over 12 f double prime at eta, which we know there exists some eta in the interval a and b. And this formula is exactly the formula for the error term of trapezoidal integration formula that I showed you before and I have computed in the previous lectures. Okay, so if you note that computing of the error term with the Newton-Cots formula error is much easier than the usual form, especially in the next case that I will show you. For the second example, let n be equal to 2. So, in fact, I want to compute the Simpson method by Newton-Cots formula, and also I want to compute the error term. Okay? So, let me put x0 be equal to a, x1 be equal to x0 plus h, x2 be equal to x0 plus 2h. Okay, here if you note to this formula, you can find out p is equal to 0 and q is equal to 2. And also we can consider h as b minus a over 2. Okay, h is b minus a over 2. Now, let me compute AIs. Okay, let me write one more times the formula here. The formula is something like this. Yeah, let me rewrite it again. We know that AI is equal to, in fact, AI is equal to h times minus 1 to power of n minus I over n factorial combination I from n integral from p to q pi k equal to 0 to n s minus k over s minus I d of s for I equal to 0, 1 and 2. I have to use this formula. So let me do this. First of all, note that n equal to 2 and I equal to 0. So a0 is h minus 1 to power of 2 minus 0. Okay, so 2 minus 0 over 2 factorial combination 0 from 2 integral from 0 to 2. We have computed p and q from here, right? And in the nominator I will have s minus 0 times s minus 1 times s minus 2 over s minus 0 d of s. If you compute this one, this is h over 2, okay? And let me see something. Yeah, it's correct. It's h over 2 times, if you cancel these two terms, it just h over 2 integral, you cancel this term, 0 to 2, s2 minus 3s plus 2 d of s, and this is h over 2, 1/3 s cube 3 over 2 s2 plus 2s from 0 to 2, right? Now you have to compute this value. This is h over 2 times, and here you will get h over 3 minus 6 plus 4, and if you compute the value in the brackets, you will get this is equal to h over 3. This is a0, right? Now let me continue for n equal to 2 and I equal to 1. So ai is equal to h minus 1 to power of n minus I, 2 minus 1 over 2 factorial combination 1 from 2 integral from 0 to 2 s minus 0 times s minus 1 times s minus 2 over s minus 1 d of s. If you compute this value, a minus will appear here and a 2 appear here. 2 and 2 will cancel, just remain 1 minus h. Integral from 0 to 2, you cancel these two terms. It remains s squared minus 2s d of s, and this is minus h 1/3 s cube minus s squared from 0 to 2. And if you continue to computation, this is minus h times 8 over 3 minus 4. Okay, and if you compute this one, this is 4 over 3 h. Okay, this one coefficient, this is the next coefficient. Let me do for n equal to 2 and I equal to 2. So a2, this is a1. a2 is h minus 1 to power of 2 minus 2 over 2 factorial combination 2 of 2 integral from 0 to 2 s times s minus 1 times s minus 2 over s minus 2 d of s. Okay, this is a plus appear here and h half will appear here. Integral from 0 to 2, cancel these two, we get s squared minus s d of s, and this is h over 2 1/3 s cube minus half s squared from 0 to 1. Okay, and if you compute this one, this is h over 2 times 8 over 3 minus 2, and this is h over 3. This is the next one. Okay, so the integral from a to b of f of x d of x is equal to, if you put a0, it's h over 3 f0 plus 4 over 3 h f1 plus h over 3 f2 plus e, right? And I can write this into this form, h over 3 times f0 plus 4 f1 plus f2 plus e. The first part here, I mean, this is exactly the Simpson formula, and I have computed it before with two other techniques. You can see that this kind of derivation for the Simpson formula is much easier than the other two forms. Okay, now it remains to compute E, the error estimate. Okay, for E, we have to use the Newton-Cots formula error term. Let me use the error term for Newton-Cots formula. Okay, because we have used the closed form of Newton-Cots formula, and we note that n is equal to 2 and 2 is divisible by 2. So we have to use this formula for E. E is equal to h to power of n plus 3 over n plus 2 factorial f n plus 2 derivative at eta integral from 0 to n t pi I equal to 0 to n t minus I d of t. I have to use this formula for computing the, error term. Now, let me do this. So, let me write E is equal to, exactly I put instead of n equal to 2. So, I have h5 over 4 factorial f fourth derivative of f at eta integral from 0 to 2 t times pi I equal to 0 to 2 t minus I d of t. Let me do some computation. So I will get h5 over 4 factorial, the fourth derivative of f at eta integral 0 to 2 t times, here I put t minus 0 times t minus 1 times t minus 2. So I will get t times t minus 1 times t minus 2, okay, d of t. Something exactly like this. So it will be h5 over 4 factorial, fourth derivative of f at eta 0 to 2 t squared, okay, times t squared minus 3t plus 2 d of t, and this will be h5 over 4 factorial, fourth derivative of f at eta integral from 0 to 2 t to power of 4 minus 3 t cube plus 2t squared d of t. Okay, and if you take integral from this polynomial, it's very easy, and you put 0 and 2 and compute compute the value. You will get the value will be minus 4. Okay, so you will get minus 4 over 15 minus 4 over 15 h to power of 5 over 4 factorial, the fourth derivative of f at eta. And if you cancel 4 by this 4, it remains just 6 times 15, it will be 19. So you will get minus h to power of 5 over 19. Okay, fourth derivative of f at eta, and this is exactly the same as I computed before with very complicated technique in the 2 previous lectures. So you can see that using this formula for computing the Newton-Cots formula is much easier than the usual technique. So I would prefer use Newton-Cots formula for computing, especially for the error terms. So let me finish this lecture and invite you to subscribe my channel and watch my videos online, and please wait for the next lecture and for the continuation of numerical integrations. Good luck.